right, so at the end of last lesson, we were interrupted by the bell. We were partway through this question. We had found the 6 equations of motion, which are over there on that last page. And we had just started on these questions here that are to do some calculations based on those 6 equations. We get to see a full one in a bit, Isaac. So there was a couple of parts to this part B. We haven't actually finished that because the question says, find how high the ball rises and how long it takes to get there. So we found the time was 0.8 seconds, and then we subbed that into our equation for y, which gave us, well, we got 3.2, but remember that our origin was 35 meters above ground level, so I had to add 35 onto that to find the height above ground level. But then it also says, how far is it horizontally from where it was thrown? What is its speed as well? What is its speed then, and how far is it horizontally from where it was thrown? 1.6. Where are you getting the 1.6? Okay, anyway. So this is talking about this projectile has gone up to the top, and we're talking about when it's at that highest point, what is its velocity and how far is it from where it was thrown? Now, remember the vertical and the horizontal components. Vertically, when our projectile is right up the top, what is its velocity in the y direction? 0, because it's going up and then it stops temporarily before it comes down, right? So the vertical speed, and squish this in because there's still a little bit left to do. So we've got vertical speed is equal to 0, that's not a 10, 0 meters per second. What about horizontally? Yeah, so the horizontal, no air resistance. There is no such voice. At least it sounds like you're talking about maths, but let's do this. I didn't see it. I was busy writing. Horizontally, remember there's no acceleration, so the velocity is the same the whole way through the motion. So if you look back onto here, our velocity in the x direction, the x dot, is the h√3, always, everywhere. So the x stands for the displacement in the x direction, y is the y direction. If you have an x with a dot above it, that means the velocity, and 2 dots above it means acceleration. Okay, so we've got the vertical and the horizontal speed. So then we want to know how far has it gone horizontally when it's at that top point. So I'm going to be subbing into my x equation, that one there, the x equals 8√3t, but what is t? How long did it take to get there? Do you remember? It's on that next page. How long did it take? It's written right there. 0.8 seconds. Okay, so I'm just going to sub in when t equals 0.8, my particle has gone 8√3 times 0.8, and you can either try and leave that exact. If you leave it exact, it turns out to be 32√3 over 5, or as a decimal, it's 11.09 meters. I don't think you need me to take the time to do that calculation again. Okay, part C. Find the time, the flight time, the horizontal range, and the impact speed and angle. There are so many parts there, so many things that we have to find. Okay, so first of all, starting with the flight time for the whole thing. Remember, okay, back to my diagram. Here's my diagram. We're starting at the origin. The projectile goes up, and it takes 0.8 of a second to get to the top there. And then, but we're going to keep going until it hits the ground. And I want to know the time it takes to hit the ground. Which equation do you think I can use to try and work out the time it's going to take to hit the ground? It's not the velocity equation, no. It is going to be a y equation though. It's going to be this one, the bottom one. Because when it hits the ground, what y value does my equation have? Nope, because where was my origin? The origin is up there, negative 35. So if I sub in that y is equal to negative 35 into that equation, I can solve for t, and that will tell me the whole time of flight. It's just directional. Think of vectors, negative meaning below, not anything else. Okay, so when, and okay, have a look at this. This is my booklet, write small, and I've got two sides to it. Okay? Okay. So when y equals negative 35, I put that into my y equation. I won't flick back on the screen again. That was negative 35 equals minus 5t squared plus 8t. And that is a quadratic that I need to solve for t. Let's put the p squared term first and positive. So let's move everything from the right-hand side across to the left. That will make a positive 5t squared, a negative 8t, and a minus 35 equals 0. To solve that, unfortunately, if you try to find the factors, it's not going to work. It's a decimal answer here. You could use the discriminant if you were unsure of how to proceed here. We will have to use the quadratic formula. Okay, so t for quadratic formula is equal to negative b. Since b is a negative 8, it will become a positive 8. Plus or minus square root of negative 8 squared. And you'll probably find, I mean, as long as you know that's a negative 8, you don't need the negative because it always gets squared and becomes a positive anyway. Minus 4 times a, which is 5, times c, which is negative 35, all over 2 times a, which is 5. Trying to keep it exact as long as I can, underneath that square root sign becomes 764, and that's when you know I can't get an exact answer because that doesn't square root nicely. So going to decimal places, you would get that time is equal to 3.56 or negative 1.96. And straight away you go, well, obviously one of those solutions doesn't work. Which one? Negative. Okay. Time is not directional, but thank you for trying. Time cannot be negative, so we disregard the negative solution. So I'm going to say t is equal to 3.56 seconds. And you can write yourself a little note there, since t must be greater than 0. That's why we've disregarded the other solution. Okay, so we've done the first part. I'll even highlight it. There you go. We've done that part, the flight time. Next part, we want to find the horizontal range. Horizontal range, that sounds a bit contradictory, doesn't it? Because range, you normally think about the y direction, but we're talking about how far have I gone in the along the x-axis. So I want to sub into my equation for x with my time of flight that I just found. So the equation was, so I want to find x when t equals 3.56. And the equation was 8 root 3t, but t is the 3.56. So that equals 49.38 meters. Okay, so that's how far we have gone horizontally across that projectile.
You need to
Okay. No, this is horizontal, 11.09.
Yeah, because that's the distance it takes to get to the H max. That's the distance it does after it.
No, that's the whole time of flight, not just from the top. Yeah, so that's 3.56 is the whole time of flight. So you you subtract off the 0.8 if you didn't want to include that first part. That's the whole time.
Oh,
Okay.
Yeah.
Okay, so we've now done horizontal range. What else do we need to find? We need to find the impact speed, and the angle means the angle that it's impacting at. So that means I need to find the x velocity and the y velocity so that I can find the overall velocity, and I'll also be able to find the angle from that as well. So let's sub into our velocity equations. So for both of them, I'm again subbing in that t is equal to 3.56. So this is right at the end point of impact. X, velocity of x is always, looking back at those equations, is always 8 root 3. It does not matter what time is, velocity is constant on the x direction. Y, however, it's a bit weird that these equations are on the other page for you, but if you look back, it was negative 10t plus 8. That was the equation that we had. So let's sub t into that. Negative 10 times 3.56 plus 8. And that makes negative 27.6. Negative because it's going down, it's hitting the ground. Okay? You can draw that as a diagram, and that will help us find our angle as well. So on the x direction, we're going 8 root 3. In the y direction, we're going a negative 27.6. We want our resulting velocity, which is our hypotenuse, so we'll use Pythagoras' theorem for that. And we're also going to find the theta, which is the angle to the ground, which is the angle of impact. Okay? So let's do the hypotenuse first. I'm going to call it v for velocity, equals, Pythagoras' theorem says, the two shorter sides squared and added together. So that equals 30.8 meters per second. Now the angle, looking at my diagram, the two sides that I have the opposite and the adjacent, so that's going to be tan, which it always is tan. Tan theta equals, opposite is negative 27.6, and the adjacent is 8 root 3. Now the negative, if you type those in, has anyone done it?
Minus 63.
Yeah. When you do inverse tan of that, you're going to get negative 63 degrees. That's rounded to the nearest degree, because that's an angle below the horizontal, isn't it? Okay, and that totally makes sense, I hope, to what that question is doing. So the angle of impact is negative 63 degrees, or 63 degrees below the horizontal. It would be in the second quadrant. If you wanted to put it above, it had to be in the second quadrant. So it would be 180 minus 63. That's the question done. Yes. You can write very small. Well done, Ben. Okay. Or this will be a good one for you, Isaac, because you'll get to see me make those 6 equations again. All right. So question 4. We have a softball player who hits a ball at a velocity of 30 meters per second, and the ball just clears a 1.5 meter fence, which is 80 meters away. That's all in the diagram there. Find 2 possible angles at which the ball could have been hit. Assume no air resistance, and that gravity is 9.8 meters per second squared. Okay, so when we do these, if we need to get our 6 equations of motion, we always have to start from acceleration and integrate to get the other equations in both directions for the x and the y. Yes, so it says that in the question for us. Yep, no, 9.8. It just says 9.8. Okay, so starting with the x direction, the acceleration on the x-axis is always 0. Now, to find the velocity, I need to integrate, which you've done a lot more in advance on this now. Integrating 0, I need to integrate that acceleration in terms of time. Integrating 0 means that you'll get not a 0. I hope that's not a 0. You'll get a constant. Integrating 0 gives you a constant because think of the opposite. When you differentiate a constant, it disappears. So if there's nothing going in reverse, it means there could have been a constant there. So that is going to be my constant number 1 when I integrate that. Now, to find out what that constant is, I need to know my initial velocities in both my x and y direction from my diagram up there. So I'm going to draw a triangle like this. Down there, right angle. And when we first did this, I did it the long way, but I did tell you that you'll probably get used to the shortcut. X is this, x dot, sorry, for velocity, is going to be the little side on the bottom there. And it's going to be 30 cos of the angle theta because it's the adjacent side, right? And the y dot, which will be this vertical side here, does anyone else want to do it?
30.
Perfect. 30 sine theta. Okay?
30 integral of cos theta.
That's right. So I now want to find what C1 is equal to. So we always consider when time is equal to 0. When time is equal to 0, or at the very start, what is my velocity? It's 30 cos theta, right? So there's no time to substitute in. I get that C1 is equal to 30 cos theta, which means my equation for velocity, no surprises here, is 30 cos theta. Because we know it's constant the whole way through, it's kind of obvious, but as I told you last week, we have to be able to derive these equations. Okay, to get to the displacement equation, whoops, no dot. To get to the displacement equation, I now have to integrate the 30 cos theta in terms of t. Now the theta, that's a 30 cos theta. No, wait a second. Velocity integrates to the displacement. So the x without a dot means the distance along the x-axis.
Oh, yeah.
You don't need it because I'm not integrating the theta. I'm integrating t. The 30 cos theta is a constant. The angle is a constant. Even though there's a theta in that equation, don't try and integrate cos to sine, which is what Ben's trying to do down here. Okay? We are just needing to integrate in terms of t, which means 30 cos theta t, but it's a bit weird to put the t after the theta because you might be tempted to go theta times t and then do cos of that. So maybe move the t further up in that line. Do you understand what I'm saying?
Yes.
Yes, good. What else have I forgotten? Or I haven't forgotten, but what else haven't I written yet?
Constant 2.
Plus the constant. Every time you integrate, there needs to be another constant added in there. Now, we haven't really discussed this yet, but where do you think the origin is of this projectile? There's not really much choice. That would have to be the origin there, right? That's our starting point. There's no height or anything. We're not going to move that around. So when time is equal to 0, how far have we moved along the x-axis? 0. So when t equals 0, x equals 0, what does that mean for C2? What's C2 equal to? Well, if t
is 30 cos theta t.
No, if t is equal to 0, 30 times 0 times cos theta, that whole thing is just 0, so C2 is equal to 0. So our displacement is 30t cos theta. So there is equation 1, equation 2, and equation 3 for my x equations. Now I need to do the whole thing again in the y direction. So in the y direction, this time my acceleration, I've been told, is equal to 9.8. Because gravity works downwards, we need to put in that acceleration is negative 9.8 meters per second. That's my first equation for the y. To find the velocity, I need to integrate the negative 9.8 in terms of t, so dt. Integrating that constant, you will get negative 9.8 t plus c, I'm going to go c3 is where I'm up to. I've had two constants already. Okay, what do I know? I need to find that c3.
C1 equals C3 equals
C3 will equal 0, but the way I know that is because when time equals 0, actually no it doesn't. No it doesn't. When time equals 0, my velocity equals, look at my diagram, 30 sine theta. That's what I worked out at the very beginning. My velocity in the y direction was 30 sine theta.
I was thinking.
Oh, sorry, 30 sine theta. I said the right thing, wrote something completely different. Because it says in the question here that the gravity, which is going to be our acceleration, the only acceleration in a projectile is the acceleration due to gravity. And so it's told us that's 9.8. Sometimes the questions will say 10. You have to use whichever one they give you.
Oh, so
Yeah, that's correct.
Does that mean 30
That's right.
does that mean 37 is negative 9.8 equals C?
Well, the negative 9.8 will be times by 0. That's not going to do anything because time is equal to 0. When time is equal to 0, okay, that means that the third constant is 30 sine theta. My equation for velocity in the y direction is negative 9.8 t plus 30 sine theta. One more equation to find, which is my displacement. So I have to integrate again. Remember, you're integrating the t, not the theta. So y equals integral of negative 9.8 t plus 30 sine theta dot dt. So the first term, the negative 9.8 t, when you integrate, you will add 1 to the power and it will become a t squared, and you'll divide that by 2. So that will become a negative 4.9 on the next line when I simplify that. The 30 sine theta, that's a constant, so it's going to be 30t sine theta plus my fourth constant. That's right. No? Okay, again, we want to find that constant. So when time equals 0, my y equals 0. So the negative 9.8 t squared, that's going to be 0 because time is 0. The 30t sine theta, that's going to be 0 because time is equal to 0. So what's C4 equal to?
7.
0. Yes, it is, but you're not allowed to use it.
I mean, unless I'm using different answers.
Yeah.
Or is it more about the process?
It's about the process. Yeah, it's about the process. Oh, wait. Oh, I'm not finished. There's still more to do in this question. We've just found the equations. That's right. Okay, so we have found our 6 equations of motion. The question actually says, find the 2 possible angles at which the ball could have been hit. I want to find the theta. Okay, what do we know from this diagram that can help?
We know something for 1.5.
We know this wall here, right? We know that when x is equal to 80, y is equal to 1.5, I could sub those into my equation for x and y that I found down here, and then I will have 2 equations involving t and theta, which can be solved simultaneously. Yep, there you go. Okay, so this is what I'm going to do. Is that okay if I can do that? Okay, so I'm going to be subbing in when x is equal to 80 and y is equal to 1.5 into these 2 bottom equations here. So for the x equation, I'm going to have x is 80, so 80 equals 30t cos theta. This is the easier equation because it's only got the one term on the right. So I'm going to take the opportunity to get that t by itself, and 80 divided by 30, I can't divide the 8 and the 3, but how about like that? I can just divide the 10, cos theta. Okay, there's one equation. Into the y equation, the y value was 1.5 equals, into this one, negative 4.9 t squared plus 30t sine theta. So if this is equation 1 and this is equation 2, I can sub equation 1, which has got t by itself, into equation 2, and I will eliminate t from my equation. So that will give me, I'm going to go sub, we've still got quite a bit to go here, 1 into 2. So that will be 1.5 equals negative 4.9. T squared is going to be 8 over 3 cos theta squared plus 30 times t, and t is 8 over 3 cos theta sine theta. Okay, now I'm running out of space here, so we're going to do some of these things in our calculator here. The 1.5, leave it there. But for that next term, I just want one number as my coefficient. So I need to do negative 4.9, leave the cos theta out of it. So negative 4.9 times 8 over 3 in brackets squared. And if my paper is correct, I got negative 34.8. Yeah? Now, the cos on the bottom there, it needs to be squared. It's on the bottom of the fraction, though. What is 1 over cos? As a different function.
Inverse cos.
Third letter, just sec. The third, so sec. So that will be sec squared theta.
Wouldn't it be inverse?
No.
Sec to the power.
Inverse cos is when you find the angle.
Yes, but it'd be sec to the power of minus, like cos to the power
Oh,
of
yes.
cos. It's the same.
Yes. You're making it more complicated, so don't do that. Okay. It is still there. The squared comes from the cos theta on the bottom, and I've got to square it because the square that's outside the bracket. Because that means a very different thing. If I have got sec theta squared, it means I squared the theta first, and then I do sec of that angle, sec of whatever that is. But when you put the squared there, it means you have to find out what sec theta is first, and then you square that whole result. They mean two different things, so it is important where you put the squared. Delete. Delete. Okay. Continuing. The next term, because it's 1 over cos, right?
Okay.
And 1 over cos is sec.
Okay.
Yep. All right. 30 times 8 over 3 is 80. No, because 30. The 30 and the 3, you 30 divided by 3 is 10, so it's 10 times 8, which is 80. And you've got sine theta over cos theta, which makes 10. Come on, trigonometry. 10 theta. Okay, I have to find out what theta is. Yes. Now, I have a tan theta there, that's nice. Sec squared, not so nice. No, because it'll still have two different trig functions in there. We can't solve an equation yet until we do some more stuff in extension that involves two different trig functions. So I need to turn that sec squared theta into a new word, into a different thing. Do you remember these? Sine squared theta plus cos squared theta equals 1. If I need 10, divide that whole equation through by cos. So it would be 10 squared theta. Cos divided by cos is 1. And 1 divided by cos is my sec squared theta. Okay, so now on my next line, I'm going to change that sec squared theta into tan squared theta plus 1, so that my whole equation can just be in terms of tans.
That would just be 0.5.
No, where's the...
Plus 1 on the end. Yeah.
Oh, I'll expand that out on the next line. So I'm going to go 34.8 tan squared theta plus 1. So just showing you that I'm changing that. And then I'm going to expand that out, which will be negative 34.8 tan squared theta minus 34.8 plus 80 tan theta. Now, let's do some reordering here. I'm going to move the negative 34.8 tan squared theta across the other side so that's positive. Yes, it is. Move the tan term next, so that'll be negative 80 tan theta. And then I have some constants. I have the 1.5, and I want to add the 34.8 across to be with it, which will make a positive 36.3 equals 0. And as Ben has so wonderfully pointed out, this is a quadratic. I have a tan squared, a tan, and a constant. So I can use the quadratic formula. I told you I had to save room here. You can use the quadratic formula to find tan theta. So tan theta equals, so you're treating the tan theta like an x. Quadratic formula says negative b, so that's 80, plus or minus square root of b squared minus 4 times a times c all over 2 times a. Not nice, decimals everywhere, but doable. That will give you 0.622 or 1.68 for tan theta. You will then still need to inverse tan to get the two angles, which will be 31.9 degrees or 59.2 degrees. Big question. But that's not the end of the question. There's still a part B and a part C on the next thing. There's only one question that we had to do today. It's a massive question. Yeah, I did a bit. Yeah. Okay, so if you've wrapped your head around that, yes? Not from the 40, oh, from the 45. Ooh. Interesting. We're going to do something similar to that in part B. It says, show that the inclination of the smaller angle from the origin to the top of the fence is the same as the inclination of the higher angle to the vertical. So we're going from the horizontal and the vertical to show that we get the same angle. But we've got the fence in there as well, which makes a difference. So what is happening is we have got our projectile here with our fence. I have a smaller angle that could, I don't know, maybe go like that to just get the top of my fence. Or if we project it a bit higher, it might come down, still just touch the top of that fence. And then there's two different angles that would still let me just clear that fence. And they're the two angles that we just worked out. We need to find, because this question is asking me to compare the angle that is made to the fence. So I need to know just directly, if I went straight from where I started to my fence, what is that angle theta that is in there? I know that from the start, this was 80, and this, yes, and this was 1.5. So we're just going to be using tan, correct? So tan theta equals opposite over adjacent, inverse tan that, and that is about 1.1 degrees. So pretty small little angle. Now, if I want to use the smaller angle, so I'm going to do the smaller, whoops, I can't spell, smaller angle, so the lower projection. If I take that smaller angle and I subtract off the 1.0, so 1.1, sorry, I rounded it. I didn't round it in my notes. 1.1. That will tell me the angle between here and here. All right, that little angle in there. Oops, where'd it go? Come back. That is not that one. Back to this one. That is equal to 30.8 degrees. If I want to use the right angle, so it says to do it from the vertical as well, which is from the vertical line there, that's a 90-degree angle. If I subtract off the larger angle, so that's 90 take away 59.2 was the larger angle that we found. That's equal to 30.8 as well. So the angle between directly going to my fence and my lower angle is the same as the angle from the right angle to the height, to the larger angle. Okay, so there is a relationship between all these angles, is what the point of all that is. And part C. Find the corresponding flight times and the impact speeds and angles. Oh, that's 3 things we have to find. We have to find the flight time, the impact speed, which means I'm going to need the X and the Y speed, so I can find the overall speed, and the angle that it makes. And it says the corresponding, which means I'm meant to do this for the small angle and the big angle. Maybe we'll do it for the small angle and you can do the big angle later.
Wouldn't the impact speed and the angle be the exact same as this and it's not raised?
We haven't actually found, oh, we have, yeah.
So 30 meters per second.
It is. You're right, because it is a parabola, it's symmetrical. Very good.
Because there's no raised.
Yeah. 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 100%. Definitely. Very good. Yeah. So let's find for the small angle. If I'm trying to find the flight time, we use the y equation and we make y equal to 0 because we're on ground level. So we're just going up and we're landing again at ground level. We just want to find how long it takes to get to 0 again. So when...
We haven't worked out the initial velocity though.
I know. Oh, yeah, we did. It was in the question. The initial velocity was 30.
Vertical and horizontal.
Yeah, well, we did it in terms of theta. Oh. Yes. Okay, so it was y equals, so 0 equals minus 4.9 t squared plus 30 t sine theta. But we know that we're doing this for the smaller angle, so I'm going to also sub in, instead of theta, I'm going to sub in my small angle, which was 31.9. Type that in, and I'm also going to rechange the order to make a positive 4.9 t squared. The 30 times the sine 31.9, what did you get?
15.
Oh, good. Yeah, that's what I had too. I just thought you said something else. Yeah. So it's 15.85, but I'm moving everything across so that the t squared is positive, and that's equal to 0. I would take out the common factor of t. I'm trying to solve this for t, and it's not surprising that I'll have that t at the front because that will give me t equals 0, which is expected, that it would be the starting point, minus the 15.85 equals 0. So we get t equals 0, and we get 4.9t equals 15.85. 3.2, perfect. Okay, so the total time of flight is 3.2 seconds. To calculate the others, and we could do it as a check, knowing that it is a parabola, Ben is 100% correct. The parabola has to be symmetrical. So if we know the initial velocity was 30, coming back down it needs to be 30 as well. And the angle of inclination, we could find that by
That'd be
subbing in. It would be the same as the start, but we can sub that in. But let's do it, assuming that we didn't know that. We'll do it as a check. It's close. So let's sub in. If this is my angle on impact, okay, so on impact, I'm going to have velocity equals, the equation was 30 cos theta, but my angle was 31.9, so that's equal to 25.47 meters per second. The y velocity is -9, I'm just putting these into the velocity equations, -9.8 times 3.2 plus 30 sine my small angle 31.9, and that is equal to -15.51 meters per second. Okay, when you do Pythagoras' theorem with those two sides, it gets close. It's because I've rounded plenty of things along the way that it's not perfect. So that one squared plus that one squared, and I came out with 29.8, pretty close. Rounds to 30 if I round it to the nearest whole. And to find the angle, if I do tan opposite over adjacent, and I inverse tan that, I get 29, no I don't, sorry. I get -31.3 degrees. And I didn't really need to do that again. We already knew that the angle that we're putting in was 31.9. But that was the process that we used for the last question. So you can see that's there as well. Okay, so yeah, it should be pretty much the same at the start and at the finish. So you're meant to go and do that all again now with the larger angle, but do we need to do that all again with the large angle? No, we're fine.
maybe reflect.
So you do it all again with the larger angle. No, the time of flight is 5.6 seconds. All right, we'll leave that one.